Welcome everyone. Welcome to this Tuesday's PCS seminar. It is a great pleasure to welcome again Professor Peter Schmelcher to present his second seminar here. And I would like to ask our scientific host, Alexei, to take over the floor. So.
Okay, thanks, Dylan. Well, basically, yeah, I mean, today, Professor Peter Schmelcher from University of Hamburg will give the second part of his talk titled From Local to Latent Symmetries and Hidden Degeneracies in Wave Mechanical Systems. So since Peter has been already talking here last week, I will skip the introduction. We all know him. So please, Peter, you can start. The screen is all yours.
Yeah, thank you very much. And thanks particularly again for this opportunity to talk about our most recent research. And last week, I have been talking about local symmetries and the impact of the presence of a symmetry in a limited spatial domain and how these led to these non-local currents and how these non-local currents could be used, first of all, detected experimentally in acoustics and optics, but also how it can be used to design systems with certain properties like perfect transmitting resonances and so forth. Now today I will move one step forward. So, and actually the concept of local symmetries is always present also here to a large extent. But then I will take a turn, a switch, and go with the help of graph theory to so-called latent symmetries. Latent symmetries are not symmetries of an original Hamiltonian, but of an effective Hamiltonian, which you obtain in a certain manner, and I'm going to tell you how in a few minutes. Yeah. And then in a second step, and actually these latent symmetries will then be heavily exploited, and we're still on the way to exploiting this massively. The main applications so far include Flatbands, compact localized states, state transport with compact localized states, quantum state transport, and so forth in certain networks. But then in the very end, or maybe the last 5 to 10 minutes of the talk, I will also be talking about so-called isospectral reduction schemes. And in this title, there is this wording of hidden degeneracies. And so that will be the part where we can understand in an isospectral reduced system how symmetries in that system relate to the original system and how that can explain degeneracies, which maybe you would otherwise declare as being accidental degeneracies. So again, this work was done with my postdoc Christian Morphonius and the advanced PhD student Malte Röntgen, and also Maxime Pisch, who joined in 2 years ago into this enterprise. All of them are at the University of Hamburg at the Center for Optical Quantum Technologies. And we have some long-standing collaborators to several of these works. Fotis Diakonos has been substantially contributing, and Nikos Paleodiamopoulos, who is a PhD student in the group of Fotis Diakonos. And then there is, on the one part, the dipolar nanocluster scattering, the Luca Del Negro, an engineer and physicist from the Boston University, who we have been collaborating with and whom we are still collaborating. And this work is funded by the German Science Foundation, which I should not forget to say, the Deutsche Forschungsgemeinschaft. Okay, let me introduce what I'm going to be talking about. First, a very brief recap of last week. As I said already, last week we have been looking into local symmetries, some symmetries that hold in a spatially bounded, limited domain. So the system is not globally symmetric, say under reflection or under translation or under rotation, but only locally. And that led to these invariant current correlators. They are in the general mathematical or formal framework embedded or come out as a special result of generalized continuity equations. That holds not only for single particle physics, but also for many body interacting systems. They can be used for various things, particularly for design of resonances, or as I have been shown last time also, for various kinds of locally symmetric systems, also quasi-periodic chains that they allow to design the edge modes in Fibonacci type systems, the homos or others. And also last time we have been very briefly touching upon the point how the introduction of local symmetries leads to a gradual delocalization of wave functions and then therefore enhanced transport in disordered systems. So now this talk will be about building up on this. In some sense it's also different, some sense it has comments. So we will use local symmetries for compact localized states and flat bands. Okay, then this is the first part. So there will be a bit of graph theory already in there, in particular the equitable partition theorem. So then we come to the point where we have a short application to open systems, open scattering systems. So, and we will see the compact localized states and resonances in a periodic chain, which is a scattering of dipolar nanoparticles. And the formalism will be the Green's function formalism, standard formalism over there, scattering from dipoles. Then in a third part, I will use what we have understood already so far from the construction based on symmetries and beyond of compact localized states in order to make quantum state transfer. You know, nowadays with all these a big fuss about quantum information processing and quantum technology coming up. Of course, you would like to have a reliable network such that you could do certain tools, such that you could do certain tasks. And one task would be to transfer a quantum state with a high fidelity in a network. Yeah? And that's what we are saying, that compact localized states induced by local symmetries might be a good a starting point because they're compact localized. Then you can make them delocalized, and then later on you can make them again compact localized. So state transfer is something which works very well, at least on the level we are dealing with at this point in time. And then in the last part about latent symmetry-induced degeneracies, as I mentioned, this is not a symmetry in the original system that can be explained via group theory, telling you what the degeneracies are, but it is latent symmetry, hidden symmetries that then share the same kind of degeneracy with the original system, but the original system might not have any symmetries at all. And just to state that from the very beginning, key to these things were certainly key ingredients, were certainly the recent graph theoretical developments, the equitable partition theorem, which we have been generalizing to the non-equitable partition theorem, the isospectral reduction schemes and latent symmetries, and there's some of these publications which are the most relevant to our work at this time. We are currently on the way, and we have done already kind of substantial steps to go further along these lines to develop the graph theoretical toolbox in the direction of what kind of physicists need to get these systems, given the questions, the physics questions, what they need in order to develop the toolbox further. Of course, I'm talking to an audience which is experts on flatbands and their theory and their applications, and there's a vast number of literature and important publications coming out of the group at IBS, at the Center for Theoretical Physics. And yeah, so let me try to add a little bit to this. So in spite of the fact that, as I said, things are well known about what flatbands are, I would like to give very briefly maybe a summary of flatband physics, some kind of flatband physics in a nutshell. Yeah. So what is flatbands? If you think about periodic system, it means that you have a flat spectrum, the energy as a function of the wave vector, typically, which you get out of a band structure calculation, it's flat. It's just no curvature. Yeah. So that implies a dispersionless spectrum. Flat means that there is no energy change with the momentum, and that of course means that you don't have a possibility for transport at first 0th order, and everything is macroscopically degenerate because all k vectors lead to the same energy. But such a huge degeneracy, as you can easily imagine, leads, of course, to an enormous sensitivity to whatever weak perturbation you have from the outside. Yeah. So one inherent, say you would have a crystal, being it natural, being artificial, which has that flat band, then of course no crystal is perfect. So you would have disorder. Disorder would lead to kind of removing this degeneracy, this complete macroscopic degeneracy. Maybe more controllable way would be to use external fields, yeah, a weak electric or magnetic or in strength adapted field that would introduce a curved band with a certain structure, would lead to splittings and so forth. So it would kind of change the flat band into a non-flat band. Ways to achieve flat bands, well, there's several, but one thing is you do parameter tuning, or another thing is you use symmetries. And IBS, Center for Theoretical Physics, has a number of flat band generators. Yeah. So the realizations, nanostructure systems, photonic systems, cold atom systems are good candidates where this has been realized, but in terms of applications, recently there's also a strong interest of flat bands in the context of high TC superconductivity. And that's a field on its own, and which is highly interesting. Pairing, like, standard BCS theory tells you pair the electrons into Cooper pairs, and which then lead to superconductivity, usually at very low temperatures. And flat bands are a candidate to induce this. So let me start talking about how can you get compact localized states, and then from compact localized states, by forming a corresponding crystal, flat bands by doing so-called local symmetry partitioning. So what is my setup? So I'm focusing on an eigenvalue problem. Yeah. So Schrödinger problem, Schrödinger equation, and then let's say we have a discrete Hamiltonian. I'm going to be focusing all over this talk on discrete Hamiltonians, which does not always mean, well, let's say it that way. I'm mostly focusing on discrete Hamiltonians, but then if I go back later to the graph theory in various contexts, this will be just a Hamiltonian, which can be visualized by a graph. And then it could be anything. It could, the background, it could be also be a Hamiltonian which stems from a continuous system being represented via a certain given basis as a Hamiltonian, which then has this kind of graph background. But let's think for a moment about this kind of a discrete Hamiltonian. And what we're focusing on, we use the locally symmetric single particle physics, and then we use graph theory a little bit in order to make some statements. So we have a Hamiltonian, and we have, of course, a diagonal that's here. It's m equal to n, the Vn diagonal elements, and we have off-diagonal elements, which, so this does not mean it's tight binding. It could be, but generically not. And actually, in most cases, we don't want it to be tight binding. Yeah. So then there's a set of...
Peter, just what do you mean by then non-tight binding in this context?
Well, not nearest neighbor only connected.
Ah, okay.
Yeah. Yes. So we have a set of neighboring sides. Yeah, they are connected somehow. One side might have one vertex might have many neighboring sides, may be connected to many of them. And then we have a non-vanishing hopping, and I will show you a graph in a minute. Yeah. So yes, so that's my point. So you have this matrix or this discrete lattice system, and you present it graphically. Yeah? That's just a mapping, isomorphic mapping. A vertex is a side, and a link is, so to speak, connecting the vertices, or it's an edge, and it corresponds to a non-zero hopping. Yeah. So in this sense, you could see it as a network, a generalized tight binding network. Physics-wise, this could be a lattice system, a true lattice system, as I mean in many cases, physics, or also condensed matter physics systems. In mapping, it can be mapped, or as a model type be approached by lattice systems, spin systems, or others, or coupled wave optical waveguides, or other systems. Yeah. So let me start with something very simple. And then consecutively, we can make that more complicated. And so this just serves as a paradigm. And then we can automatically imagine that this goes further, even making it larger, more complicated, more links, and so forth. Yeah. So simple system. Let's take these 3 vertices. This is a graph. This would be a 3x3 matrix, which would describe this graph. As you see here, there's an H prime link here, there's an H prime link here, there's an on-site energy V prime, and the colors tell you it's the same on-site energy. And so these two, the side 2, or the vertex side 2 and the vertex 3, they have the same on-site value, yeah, in the graph. So that is obviously invariant onto permutation. You permute 2 and 3. And if you take this permutation matrix and if you commute it with the matrix H, represented here in terms of a graph, then you will see that that commutes. Okay, so the eigenvectors have a definite parity. That's, if you want to view it that way, that's the global symmetry of this very simple graph, or of this 3x3 Hamiltonian. So this is a commutative symmetry. Obviously, it commutes with the Hamiltonian, commutative local symmetry, because what you exchange only 2 and 3, and you leave 1 as it is. But then, if you think about this, yes, there will be eigenvectors having a positive parity and a negative parity with respect to sides 2 and 3. But negative parity, or negative parity overall, means that this side has to have a 0 amplitude. Yeah. So in this sense, that is a compact localized state, because it lives on sides 2 and there is compact localized states which have odd parity here, living on sides 2 and 3 and having amplitude 0 on 1. There's of course also other states, and I will come to that in a second.
Professor Schmelcher, we have a question from Ihor. Ihor, please unmute yourself.
Hello. So
yes.
I didn't quite get this part. If the symmetry is local and on the accent sides 2 and 3, why then antisymmetric eigenvectors should have 0 amplitude on side 1? If the symmetry doesn't even affect, because
yeah, well,
doesn't.
Yes. Well, whether you call this here a local symmetry or not, yeah, that's you could call it also global symmetry for this one, but it is the eigenvectors. Actually, maybe the best is if you wait for a second, yeah, because it is all embedded in the equitable partition theorem. But just as say stating it right now, I mean the next page there will be the full statement. But stating right now, there is this block structure which emerges where you have the antisymmetric states impeding nodes on the other sides which are not involved in the symmetry transformation. Yeah. So let me, maybe this becomes clearer if I switch to the next page. And I'm sorry for this math over here. But I think it's good if you see it once at least, yeah? And so you can go into that and explain what you have a local symmetry. That symmetry operates on a subspace, and it is a certain number of symmetry operations. You can define orbits, you can define their size. These are all the kind of tools which people do in graph theory. I don't want to go into the details of this, but I wanted to show you once the strategy, how you analyze systems that have this kind of local symmetry, which is now in this case a commutative symmetry. So basic commutative local symmetry, yeah, S of order K. So what do? This is the original Hamiltonian. Just by reordering rows and columns, you can structure it in the following way, yeah, such that there is an F over here, a G dagger dagger over here, a G here, and then the C matrix is over here. So that is always possible. That's nothing which scales badly. It's just a resorting of your matrix. So it's almost, yeah, let's say call this a trivial step or not, but this is the structure which you get then. So then you take this, and then the statement is there exists a unitary transform. There exists a similarity transformation, non-unitarity, which brings this to block diagonal form. There's a block R, there's a block B1 to a block BK minus 1. And the block the block R has the F in it. See, this is the F from the reordering here. It has the G in it. That's the G which is up here, yeah, which you know. I'm pinpointing because we know all of that. There's a B0, and the BJs are all combinations, sums of CMs, which are these Cs, yeah, times phase factors. The phase factors either e to the pi I over k, and you take the power to the j times m. So what this tells you is, well, I can make my system due to the existing symmetry into a block structure. The block structure has a block R and B blocks, which come from these matrices C0 to CK minus 1 with some phases. Okay, so that, as you can easily imagine, helps already a lot, because my eigenvalue problem will be decomposed into eigenvalues which are eigenvectors which have belong to these different blocks. So if we decomposed, if I know the eigenvectors from B1, from BK minus 1, from R, I can make the total eigenvector.
Professor Schmelcher, Ihor has further questions.
Yes, please.
Could you please clarify what is order of symmetry?
The order of the symmetry is the number of non-trivial symmetry operations. Yeah, now, because generally the symmetries over here are permutations. Yeah, as I indicated here, you permute 2 and 3. Of course, you could see it as a reflection, but then it depends how you draw your graph. So permutations is the key, permutation symmetry. Yeah, and the number of non-trivial permutation operations in this symmetry group is the order.
Mm-hmm. I see. And
yes.
And the size of these blocks, it's connected to K somehow, of the GC blocks?
Right. It's connected to K, yeah.
Okay, thank you.
Yeah. Now, let me...
excuse me, we have a further question from Alexei.
Please.
Yeah, sorry. Yeah, could you please go to the previous slide? So what are exactly the matrices F, G, and C?
Well,
so
you have the original kind of graph and Hamiltonian, and the statement is you can do a reordering of rows and columns such that it has this appearance.
Okay. Yeah, and then the second...
There's something here, and there's always the same thing here, always the same thing here, and so forth. Yeah.
Okay. Yeah, and the second question is
just maybe a side remark. I mean, these C's involve, of course, certain sites. Yeah, and if you know already where your kind of local symmetry is, then you would reorder these, because this block here has to do with the local symmetry, yeah? And this block has to do with the rest.
Okay. So my question is, so you to block diagonalize the symmetry adapted Hamiltonian, you use a non-unitary transformation. So does that imply any consequences? Because usually we like to deal with unitary transformations.
Not.
So are there any caveats at this point?
No, not.
Okay.
No. That's just this general space which because this is all, it's a similarity transform. You just diagonalize a problem, or you block diagonalize. That's it. You have a general matrix, yeah.
Okay, thanks.
There is a further question from Ihor.
Sorry if I'm taking too much time. Just trying to understand intuitively this structure. Is it possible to easily see what will this block structure be for the examples from the previous slide?
Yes, I think, I mean, if you move one step further, then you will see, then you will see what the eigenvectors are. But as I said, I mean, from this very simple thing, these two sides are involved in the local symmetry operation, yeah? So that means the F will be only a single number, yeah? And the C2 will be the block which contains this symmetry operation, yeah? Yeah.
And G?
If you make this larger, like indicated here, for example, actually, I should have said that. This is a step from here to here, where you enlarge the original graph. You put something which is kind of linked to this V1 side, and you can do whatever you want here. The local symmetry is maintained, this one over here, and the commutation is maintained, and therefore the local parity is maintained. So, yeah, let's go to the eigenvectors, because this is then a part of the key information. Then the statement is that there is capital N F plus K times L. Now, what is that? F is F, K times L is this kind of dimensionality. Yeah. Eigenstates of the matrix, and this is the F is the ones that are not in the symmetry involved, trivially unchanged by symmetry operation. K is the order of the symmetry. And then there's all the number of non-trivial orbits, which is the L, which is the number of sets of symmetry closures. And then these are and this is the key, these are the eigenvectors. So there's fully extended eigenvectors, and there is eigenvectors which have zeros on the F sides. This is the sides not involved in the local symmetry operation. So these are those sides down here, yeah, in the general case. And then there is these entries which are which are non-zero on the sides which are involved in the symmetry transformation. Yeah. So, and then you can, of course, you use the block structure, you use the eigenvalues of R, you use the eigenvalues of the BM, and the fact is that the vectors which are given here are compact localized on S. S is the space, the isolated subsystem. That's why it is partitioned, the isolated subsystem on which the symmetry operation takes place. Yeah. So statement, the first F plus L eigenvectors of H are symmetric under S. The remaining K minus 1 L eigenvectors are both compact localized and not symmetric under S. So now we have been actually picking this up and doing things with it, but in a second step, we have been extending it. What I showed to you before were commutative local symmetries. Now you can generalize this to non-commutative local symmetries, which is actually not a symmetry at all if you look into the corresponding graph. And this happens, for example, here, if you have a different gamma 1 and gamma 2. So that would be locally symmetric. If gamma 1 would be gamma 2, then it would be a kind of locally symmetric. But then if you make gamma 1 different from gamma 2, this is not locally symmetric, but still there exist compact localized states, and that goes back to this non-EPT, which is not covering or the rest of these cases where there's no local symmetry, but it is a special case of a non-commutative local symmetry. And again, then you construct these extended states and the compact localized states again, while from the formulation, which I showed you here, there's some small or minor deviations. The eigenstate properties do differ to some extent. Okay, so let me move a little bit with knowing this towards applications, yeah? Towards, okay, you can form out of these compact localized states, of course, also this is compact state, flat bands. But let's not do this at this point in time. Let's just focus for a minute on the band structure of a periodic lattice and introduce a tailored perturbation. Very simple example. Yeah? So a local perturbation, which then introduces a local symmetry, and the game and the aim is that it should leave the band structure intact. Yeah. So usually, if you introduce a perturbation into a this kind of perfect crystal, what it leads to a localized state and therefore a defect mode, and that has an exponential decay, and that changes the overall spectrum. So let's insert a dimer over here, yeah, as it is shown over here, yeah. So we have this dimer, and we have the extended lattice outside, and the two sides or the two vertices are coupled with a link with H2, and then there's a coupling to the lattice with an H1, yeah. If this is a commutative local symmetry, then the equitable partition theorem tells us, well, that's a linear chain with a defect, but there is, due to the local symmetry, also a compact localized state, which comes from, again, the anti-symmetric situation of the eigenvector. Then, if we also additionally adapt the defect parameters, then we can end up, and this is the statement, into an unperturbed chain plus a single compact localized state. And this can be even reduced to, and then this can be changed such that you can move energetically the bound state to a bound state in the continuum by moving the energy of this one compact localized state into the band. So in this sense, this is then a defect which is invisible, which has no backscattering. Yeah, that's what it is. Yeah. So first scheme is introducing this local symmetry, getting the compact localized states, second step tuning, such that the original band structure is maintained, but still there's the compact localized state, which can be moved to the corresponding band. Yeah, well, of course, what I've shown you so far is very simple setups, but you could arbitrarily generalize this. You could introduce different degrees of complexity, connectivity. The graph theoretical result is there. You can design the local symmetries. Let's do it with a piece of a band structure, with a piece of a lattice. Again, here coupling, and then you have two pieces here. Then you can see you have the local symmetry, which you can have here in terms of reflection, as you can have it over here. And then you can systematically reduce the state space, as we did with the equitable partition theorem. And then you can position multiple compact localized states that finally become invisible to the host lattice, or can be moved again to the band. Yes, you can do it also for the non-EPT, where originally you don't see a permutation symmetry over here. Yeah, so you would not approach this with a symmetry-based intuition, but still a non-EPT tells you, based on these non-commutative local symmetries, that this decomposition, which is this root over here, is possible. So there is already on this level a way of generalizing systems in aperiodic lattices and systems with inserts of non-trivial, non-commutative symmetries is such that you can get bound states in the continuum and move them around. you could do that, of course, also in higher dimensions and not just in a single spatial dimension. Yeah, so what about flatbands? Of course, the idea is you periodically continue such an element which has a compact localized state such that you obtain via Bloch finally the flat band, because it's infinitely many compact localized states which then add up in their linear combination to the delocalized states, which all are degenerate. Yeah. And so whose energy is independent of the momentum of the maybe kx, or if it is 2D lattice, kx and ky. Yeah, the non-EPT can then be used to design a prescribed number of flat bands at desired energies. You can move them around. So you can go in 2D, you can go this by extension in both directions like it's done here. And then you get, of course, 2D flat bands, as you can see in this stack. Yeah, here's one, yeah, and here is one, yeah, and there's in between one, like here, yeah, and you can do that simply by systematically taking the local symmetries in here, which is like, for example, here, and do your business EPT, and here you can see it in a serial connection. Or this is a parallel connection instead of a serial connection, where you can have the flat one here and the flat one over here. Yeah, there's also possibilities to move this off such that there is no crossing here by adjusting corresponding couplings. Okay, so this was a bit of the framework. Yeah, so based on what EPT tells us and generalizing it to non-EPT, we have a way of approaching the flat band compact localized state systematic symmetry-based construction, and then its generalization and appearance of flat bands in a periodic correspondingly arranged manner. So now this was kind of in 2018, and then at that time we had already started collaborating with our collaborators in Boston University, Luca Del Negro at engineering, and he is an experimentalist by education, but he's very deep into theory also. So we started out, let's not do that case only for this Hamiltonian system, but let's make a step into kind of modeling of nanostructured particles, of nanoparticles. And one step is to do it with kind of dipolar systems. Yeah. So this is now a photonic setup. Yeah, maybe you had in mind over here more the quantum mechanics setup. I don't know, but what's up now is the photonic setup. Yeah, so that's a bit of different because, of course, electromagnetic fields are vectorial quantities. You have electric, you have magnetic fields. So things are a little more complicated. There's polarization and so forth. And interactions can be long range in particular also. So it's not only your next neighbor which plays a role. So you need to determine the response, the electromagnetic response of a chain. And we did that on the level of dipolar character. And as I said, the electromagnetic interactions couple together all particles. Yeah. Yeah, so in the design here, all kinds of geometries would be possible. That's a good point. Like it is also possible and more recently in cold atom systems by optical tweezers where you can arrange individual atoms. And the idea was a little bit of the motivation. Well, there's bound states in the continuum. Those are used in optics and metamaterials in order to do different things. One of them being kind of ultra compact solid state lasers, sensors, narrow band filters. So this is in this engineering side, in the photonics branch, going quite a bit into applications. And our the approaches which you could take is, of course, first of all, time binding. Again, that would be a step back. But the issue of for us at this point was to do an intermediate type of calculations. Instead of tight binding, you could go to the full vectorial numerical simulation of the photonic structure, including material properties, including the full propagation of the field, but that's expensive, yeah. So we decided to go to something in between, which is actually Green's function based, yeah. So there's a standard Green's function based scattering toolbox that includes multiple scattering. It's not just a Born approximation where you have a single scatterer and you have an in-out, but it includes the full vectorial multiple scattering properties. And we combine that with our knowledge, which we have from locally symmetric versus graph theory. And what we did is, you know, before I took the Hamiltonian, I mapped it on a graph, and I do the block structure. As rightly commented, this kind of symmetry adapted block structure. So what we now do is we do it with the dyadic Green's function, which is the key quantity in this project. Yeah. So it was a bit of work, not just immediate transfer. One has to think about this is vectorial components, so you have to be careful. But when you do it, then you learn a lot about the system. Yeah. So in particular, this gives you then EPT, non-EPT, access to eigenspectra and eigenvectors of extended states, but, and this is where we are most interested, in the compact localized states and the resonances. So you can, and this is an open scattering problem here, you get the quasi modes, quasi because it's an open, and they are embedded into this open scattering problem, which is in general a 3D thing. Now, just as a comment, there is limitations to this Green's matrix method, but people have it very well under control. Since we are not too much experts on it, we used also, of course, this was what the collaboration was for with Luca and his team. And so what it is relying on is that the wavelength is larger than the distance between the particles. And I'll say the particles are much smaller. So you have kind of small scatterers compared to the wavelength light. And then this limit, each scatterer can be traced back to a Breit-Wigner resonances. And this is one such setup. You know, we have vectorial components for each side, and then they are linked together. It becomes already a bit of messy, which is zero, which is non-zero. There's some intrinsic structure and so forth. I don't want to go into the details of this. I just want to show you, again, quite a simple setup. It's 500 nanoparticles plus 2 scatterers, and we're going to exploiting the symmetry with respect to the reflection around the axis of the many aligned scatterers. So the y direction, y to minus y, reflecting around the x-axis. So this is the setup. And we were interested in the mode spatial extent, which is a kind of reminiscent of localization measures like the inverse participation ratio, slightly differently defined, but it also tells you how localized a mode is. Yeah. So what is shown here is as a function of the optical density, the frequency and the decay rate, because this is an open system. And what you see, first of all, that it increases monotonically here and it decreases here. And what you see is that towards zero optical density, there's these kind of heavy oscillations, which you see also here. And in the inset, this is enlarged. You know, this is a smaller scale, 1 up to 0 up to 5, 0 up to 5. So you see this. And if you plot it in the graph of omega versus gamma, you see this spiraling. This spiraling is a proximity resonance effect. Yeah. What the most important thing from B to D is to note that there is that you can see here, first of all, the very well agreement between numerical and analytics, which comes from our modeling and using the EPT, and then also that you get these complex localized states. That's the typical behavior which you expect from those. And then you see it also graphically if you look at this plot, which is a bit of kind of not overloaded, but you have to look at it in silently to see it. This is a side number. So this is the device. This is a parameter changing. This is the optical density, which is actual the number of scatterers per wavelength, yeah, as a measure for the density. And what you see is that this is the localization on the two sides. These are the compact localized states, yeah, and these are the spreaded ones. So you see there's a state which is compact localized right away on these two sides where we have the two sides A and B. And then you can change dy actually. You don't remember what dy is. dy is this distance. Now changing dy, here this graph is done the way that changing dy is the upper part and the lower part. Yeah. So that means if you come to this, you have q is actually the normalized quality factor. Yeah. That tells you how much you're localized and how much your lifetime is. If q is large, you have an excellent lifetime and little decay. Yeah? And so you go to this peak, and at that peak, this is where your compact localized state lives. This is reminiscent of this one down here. And then you see changing the geometry, because dy changes the geometry. This is the symmetric configuration. Yeah, and if you go out there, this is a highly asymmetric configuration. Your Q value is very low. So this is the corrector for resonance. Yeah. And now this is done here for the regular chain out here. You see that? If you move to the disordered chain, you know, this is, you see this, that this is kind of fluctuating distances, then you see that there's still such a peak. This kind of, even at the disordered chain, this local symmetry is there, and there is a compact localized state. And then you see also this resonance over here, the peak, the steep peak in the Q. That's a logarithmic scale, by the way. And that happens again once the symmetry is restored. And once the symmetry is violated, this is the point out here, you have a very small Q. So that gives you kind of an example of a dipolar nanoscattering case, the link that things that you get from a pure, maybe graph theoretical underlying approach and applying it to your Hamiltonian matrices or your and is also backed up by more complicated, more realistic approaches, which is in this case the Green's matrix formalism to the dipolar scattering. Yeah, I mean, at some point, of course, one might think about that these compact localized states, since they do not couple to the environment, might also be a good point for quantum state transfer. Because if you don't couple to the environment, of course, in reality, you won't do that. You will always couple, but say in this kind of at least zeroth order picture, which we have, then you would get no decoherence of that state. Yeah, it wouldn't decay, it wouldn't disperse, it wouldn't couple to the environment. So then the next step is, okay, can we use that such that we design a compact localized state, and then we do something with our system and let it move somewhere, and then maybe there's a way to form at another place a compact localized state. Yeah, so that would be storage on the one hand side and transfer through a network of compact localized states. So that would be, of course, of relevance for quantum networks, maybe for quantum as a piece of a quantum computer or simulator or whatsoever, which is a big hype nowadays. Of course, there is a conflict here. Yeah, storage implies decoupling from the environment. Clearly, we can design that. That's perfect for CLS. Then you're protected against imperfections. I've shown you very recently, or a minute ago, even if the system outside is disordered, you don't care. The local symmetry gives you the compact state. Then you have to do something. You have to couple to the environment to make a transfer. you have to interact with the environment. That would lead to propagation through a network. And let's do that, all based on what we have seen so far. So several key ingredients, yeah. CLS, perfect state transfer, optimal control theory. All that plays into this game because, of course, I would like very high fidelity for the transfer. Maybe I achieve that only if I do kind of optimal control of whatever, yeah, maybe of making phase flips or maybe making changes of the link strength of the hoppings, yeah. And all of that is I'm going to show you a few examples. So one idea, again, to emphasize, maybe you do a phase flip of your compact localized state, then it starts dispersing because it's not a compact localized state anymore. Then at some point you do a phase flip again, maybe miraculously your state has been transferred, or you do it with a driven time evolution of links. We will do both. So let me show you a few, that's not real movies, but I will walk through this. What you see here is a simple chain with couplings. Then there is this kind of modified chain with a dimer at the ends with certain couplings. So that has, if this is symmetric, a compact localized state. Yeah, see that one. Yeah, that doesn't couple to the environment. Now let's make, you see what I did? I changed this coupling. Okay, so let's see what happens. If I'm going to be moving, you see I'm moving to the right, and then I am going to the right here, and then I'm here, you see that minus sign, and then I switch, and then it is stored over here. In this simple chain over here, if I move further, I would simply be reflected and I would move back to the beginning. So this was one setup. Sorry. Let me show you a second setup. So this is a kind of a, I don't know, a configuration where the dimer has been introduced at the second side and somewhere here, yeah. And then I have couplings J prime and J, yeah. And then, so let's start with this, yeah. So now what you see here is I'm going to be moving my compact localized state, yeah. You know, it was at the beginning here. Then I change the couplings J prime J, that is these two red and blue colors. And I will show you here the time dependence and how it moves to the right-hand side. Yeah. So you transfer it, see how it moves to the right-hand side. And then at some point, it is stored on the right-hand side and you go back to the original configuration. Okay, you can do that not only with such a simple chain, you can do that with a network. And we decided to go for a Lieb lattice. This is a Lieb lattice, kind of a hollow lattice with a square lattice. And then we introduced dimers. So it's a substituted Lieb lattice. That's why we call it decorated. And our aim is to make compact localized state storage and transfer. So let's start with a CLS, for example, here, yeah, with a plus minus, yeah, which lives only on these two sides, yeah. And then the protocol would be, or there's many protocols, but one thing is, of course, within such a star configuration, and actually the star configuration, as you can see here, is the elementary building block of the system. If you look at the star configuration, what I would like to do, get a CLS transfer from left to right. Okay. Overall, we use different protocols, as I indicated, also optimal control. And I don't mention this again, I just mention it here. Of course, you have to test everything with respect to robustness, fluctuations of J values and so forth, on-site energies. And it turns out all the things are quite robust. So, but what about the transfer? Yeah, you know, one way of transferring it is you start with plus minus here, and then you do a phase flip. You do it to a plus plus. It propagates, and it comes to plus plus, and then you flip again, and it becomes plus minus, and it's a compact state again. And here you see the occupation, yeah, of the sites the width here is giving you the occupation strength. So you see it decays here, it decays here, the immediate one, the central one is occupied here, and then the final sides are occupied. And you can do it also with a J-flip, yeah, not a phase flip, but a J-flip. Yeah, J is here, minus J. These two are changed now, you know, these double links. And then you propagate, because your compact localized state is not a compact localized state in the new lattice anymore. You move over here, and then you go back to original J configuration, and you have your compact state. And then this is the more complicated. You could do that example also with CREP, which is an optimal, goes back to Tommaso Calarca in his group, Antonio Negretti and others who have been developing this. It's essentially a randomized basis, Fourier component basis, which optimizes within a few Fourier components the transfer. And then you see you have these J's that vary over time. And this makes you a perfect transfer with a fidelity, which is 0.99 something. Yeah, equally, this can be extended, of course, to a lattice. No way, no problem. And you make out of this a Lieb lattice, yeah, extended lattice in all directions. And this is a 2D, and then you have a flat band. And you, as I indicated previously, you can also change, because the original one, which I have been indicating, would have cones touching here. Then you can also make an energy gap here by changing the couplings. Okay, so let me show you how you move with this optimal control through your lattice. We start here with 3 compact localized states. You see them here. And I want to transport them somewhere in the lattice simultaneously. Okay, let's do that. You see in the course of this pseudo movie how the switching goes, because the links are missing. If I switch off gradually and switch on, you see also the phases of these links with, sorry, with the blue and the red color. You see the occupation, how this is moving through the lattice and is becoming compact states. And that's the final state. Yeah. So you see, we have moved things quite a bit through the lattice by exploiting this switching procedure. Okay, I'm coming to my final chapter, and this is now using a different part of graph theory. As I indicated, we are developing this part also heavily for the purposes further, both the graph theoretical fundamentals, in order to have more applications in physics and get deeper and deeper into the possible structuring of systems. And this is the latent symmetry-induced degeneracy. I think we do not need to discuss a lot about whether degeneracies are necessary or not, but I think degeneracies are all over in physics. We have the Antella quantum Hall effects, molecular physics in condensed matter physics, and with macroscopic degeneracy. Flatbands are one, actually. We have conical sections in molecular systems. And all of that, however, is mostly based on group theoretical things where you can use symmetries in order to predict the degeneracies. And what you need is a non-abelian group character in order to induce a degeneracy. Otherwise, and this is maybe the typical thing how you say it, otherwise you would call it an accidental degeneracy, which we know you can vary parameters and you can introduce degeneracies. Von Neumann-Wigner have done that, predicted that very early, and they told us how many parameters we need in order to get a degeneracy, for example, of a potential energy surface of a molecule for a conical intersection. So here the viewpoint is different. Here we do a symmetry analysis of an effective Hamiltonian. So we do a reduction of our system to an effective Hamiltonian such that the reduced effective system is isospectral to the original one. So you have the same spectrum, okay? So then if there's geometrical symmetries and if we have an apparatus for the effective Hamiltonian predicting degeneracies, and if we can show then that degeneracies move back and forward, then we have a handle on understanding symmetry, understanding degeneracies in the original system by understanding symmetries and of the reduced effective Hamiltonian. This is what we call latent symmetries. And this is the main ingredient. As I said, we are developing this further. Latent symmetries are not visible in the original system here. They are linked to local symmetries in all powers of the Hamiltonian. That's a good point, yeah? So a key to a diagnosis is the powers of the Hamiltonian, yeah? So this is telling you that you have these kind of latent symmetries also. It's a way of probing them, yeah? Okay, so non-abelian latent symmetries are induced by rotational symmetries. Now that's the first step I'm going, yeah? It's not the only one, but let me do that as a first step. So non-abelian latent symmetries are induced by rotational symmetries in the original Hamiltonian. That's the first step. So I do have a rotational symmetry in original Hamiltonian, which however is not sufficient to explain the degeneracy. Like for example, a C3 symmetry, that's an abelian group. You don't get in group theory a degeneracy. Well, then time reversal invariance will come into play and will kind of not add to it, but we will see that if you go to the effective Hamiltonian, you will see the non-abelian symmetry, which is responsible for the degeneracy. Then in the second step, we can break that rotational symmetry in the original system. So it's even not there, and still you have the latent symmetry and the degeneracy. And we can even generalize things. So what is the scheme? The scheme goes as follows. The isospectral reduction scheme tells you, if I have a matrix A, H, yeah, then I can do the reduction scheme. S, this S is the number of sides which are involved in the symmetry operation. S bar is the complement. So we have a effective Hamiltonian, yeah, which is given here, yeah. An effective Hamiltonian defined as follows. It's H, the original H on that subset, SS, minus the coupling of between S and S bar, then the S bar, which is the non-symmetry involved propagation. You see, it's like almost like Dyson type equation, minus lambda 1 over I to the minus 1, and H coupling back. It's a more Feshbach projection operator, H S bar S thing, yeah. So what you see is that you have an effective Hamiltonian in S given by HSS minus coupling to S bar, propagating in S bar S. Now propagating doesn't mean in time, it's just kind of a visual, kind of a picture. So, but this tells you, this is a Hamiltonian, that this is of course highly nonlinear lambda. In the beginning, we have a linear eigenvalue problem. Now it is a highly nonlinear eigenvalue problem. Yeah? And like, for example, this one, very simple starting example. We have this graph, we have the links, we have the on-site energies and so forth. And the reduction brings it down to a graph with only 3 sides. And these 3 sides are all equally coupled and have the same on-site energy. The coupling is lambda dependent, not only on Hi and Vi, but lambda dependent. So this one has a full D3 symmetry. This one originally, if H1 and H2 are different, has only a C3 symmetry, but no reflection symmetries. Yeah? So this one is a larger group. It's a non-abelian group. It naturally has a degeneracy. Yeah. Okay. So actually, there's 2 doubly degenerate eigenvalues here. And then, and this is what you have to show, that transfers back to the original Hamiltonian. That means this has also is doubly degenerate. Now, in this context, this is sort of reminiscent of having a C3 abelian plus the time reversal invariance, yeah, which causes, or which is kind of linked to degeneracies. Yeah. Okay. Now, from that, you can show the following, generally speaking. Non-abelian latent symmetries of the isospectral reduction lead to degeneracies in the spectrum of its nonlinear eigenvalue problem. And in the non-abelian latent symmetrization necessarily induced degeneracies onto the original eigenvalue problem. That's what is underlying this approach. Okay, let me link a little bit these two local symmetries. I'm talking about latent symmetries because in the effective Hamiltonian. In some sense, if H features a latent symmetry, which means there's an RS of H here with these symmetries in the reduced case, then there exists of matrices M which commutes with RS, and then H has to be also locally M symmetric. Yeah? This doesn't need to be permutation symmetries, and maybe in the more fascinating cases they are not permutation symmetries. Yeah? And then the key is that then for all powers of H we have the commutation, of course, of H with Mi for all I. And then also think back, this is the original H. The K power of H does commute with this Mi. And that's the way of detecting latent and local symmetries. Okay, now you can start doing that with more complicated things. This is a graph which has no permutation symmetry. You can do an isospectral reduction over sides 1, 2, and 3, and you will see you will have a latent D3 symmetry, and you have doubly degenerate eigenvalues for any choice of H1, H2, which is meaning that there is no original symmetry in the system, in the H, and H1 and H2 can be arbitrary, and they are indeed maybe a way of symmetry breaking here. Symmetry is broken, but latent symmetry tells you there's degeneracy. And now you can move with this, of course, to lattices and introduce systematic degeneracies into lattices, yeah, which I won't do actually for a lack of time, which I've anyway been using exhaustively. So yeah, that's it. I hope I could convince you that graph theory is useful also in this context of flatbands and degeneracy explanation and further design. Design also of bound states in the continuum, but also other issues, that it can be used for quantum state transfer, that it can be used also for extended systems, maybe shifting around cones of intersections and so forth. Yeah. Okay, with that, I would like to conclude and thank you very much for listening.
Thank you, Professor Schmelcher, for this nice talk. Let's thank our speaker. Now we have time